So I mean just kind of a motivation slide. Yeah. So this always I use, and of course I also used it for my the PhD defense. So it's almost 6 years or 15, right, almost 10 years old slide. Yeah. So basically here what we are trying to really say that, right, so in the past, right, so we were able to kind of or right, our the seniors or whatever, right, so they were able to really build even computers with this vacuum tubes, and of course, right, so none of us maybe studied these vacuum tubes, right, and then the era of the discrete transistor came. I mean that's where now we have, let's say these discrete transistors, and we were also kind of able to kind of create the let's say the computers. And then soon after that, what is known as the integrated circuit era started, where not only the transistors but their interconnections were started realizing on single piece of silicon. So now we call it as everything is integrated. And then of course, right, the companies like in the beginning, right, so Apollo, Xerox, and of course, right, we know only Intel, but these are the companies they used to really build the PCs, and of course, right, so Intel gained the momentum and then started building Pentium 1, 2, 3, 4, and of course, right, after that something happened, we went into the multi-core era and all. So here the idea is that the transistor density, right, is kind of doubling almost every 18 months or the 2 years. That means maybe the physicist, chemist, or the lithography people, or maybe the fabrication equipment people, right, everybody is really working towards only single aim. How could we really kind of reduce the size of the transistor so that we can pack more and more, and if you have more transistors, it's more powerful, we can do multiple things. That's the idea. And actually, right, so the Moore, right, it's a not a kind of law or anything, but it's a more of an observation, right. So everybody is really working in a kind of a tandem to really increase the count. And now from our perspective, what is important is that, okay, so this electronic design automation tools, right. So right, so here I mean since we kind of decrease the transistor sizes, right, definitely the distance between your source and drain will definitely decrease, and again you see, right, the distance is decreased, right, of course, right, the speed is almost constant for the electron, right, and then of course definitely the time will decrease. So ultimately the clock frequency goes up, and that's where it started shooting up the clock frequencies. So maybe let's go back and check. So what are the frequencies of the Intel Pentium 1, 2, 3, and 4? Okay, good. So here, so electronic design automation really plays a kind of a vital role. Okay, now let's say, I mean in the lab also, right, if there are multiple components, right, at some point of time connecting wires on the breadboard will be really difficult and it will be messy, right. So here the same thing, right. So we are trying to deal with millions and billions of transistors, right. Suppose if I ask you, right, so you wanted to draw a full adder, perfectly fine, it fits in a kind of a piece of paper. But now if you wanted to really draw a kind of the diagram of the complicated processor what we have today on a piece of paper, it would be really tough, right. So basically, right, so these electronic design automation tools will really help us to really kind of design block by block, and maybe they help us really kind of comprehend the designs, right. So that's where this era of VHDL, Verilog, and of course, right, the front end tools, back end tools really started emerging. And now if you see, right, without those tools, I mean you see, right, we won't be able to kind of do much today, right. So that is really the importance of the kind of electronic design automation industry. And again, of course, right, I will say that synthesis tools are really the kind of at the forefront, right. So maybe you write your Verilog or VHDL design, but of course, right, we need someone or some tool to really translate that Verilog design into some kind of a gate level netlist, right. So the synthesis tool is the first tool we'll try to use. Okay, good. I just wanted to really motivate that. Okay, so this electronic design automation tools or this industry is also kind of one important industry, those who are looking for the career in VLSI. Okay. So as I said, so I will not go into the kind of each and every details of the language aspects, and I'll just kind of pass on the slide deck. You can have a look. Okay. So as I said, so we will only look at some important things. Okay. So then we can do it this more interactively. Okay. Now if I ask you, right, okay, So what are the two important constructs that you should know in Verilog? What are the answers? Okay, right. So any design, right, in a digital design, we can divide it into only two things: combinational design and a sequential design. Okay, now to do that, of course, right. So how do you really model your combinational designs and how do you really model your sequential designs? Okay, now you tell me what are the kind of constructs available in Verilog that you should know to kind of design your combinational circuits as well as your sequential circuits. Srikhar? Okay, so what are the two important constructs that are available in Verilog for to model or the design combinational circuits and the sequential circuits? I mean, those are like different abstract type or the way you can describe your design, right? Okay, I'll just kind of help you out. So there is something called continuous statement, right? So what we call it is a continuous assign statement. So basically we are talking about assign statement, okay? And there is something called procedural kind of blocks, right? So what are the procedural blocks in Verilog? Always and initial, right? So why we call them a procedural blocks? Okay, right. So if you understand the difference, I mean, learning other things would be really easy. Okay, good. So as I said, right. So I mean, as somebody answered, so there are two procedural blocks. So initial and always, and again you see, right, initial we will not use it in a real design, right. So to initialize the signals in the test bench and all, we'll use the initial block, right. So only the always block, right. So which we will use, okay, in the real designs which are synthesizable. Okay, and we'll look at in a minute, right. So why we call them a procedural kind of a blocks. Okay, so here, okay, so before let's say go into the details. Okay, so now for a combinational design, right, as you mentioned, okay, so we will use what is known as continuous assignments. Okay, and for the sequential designs, so we'll use maybe the always block, and of course, right, we can also use always blocks to really design a combinational circuits. Okay, before going to that, maybe if somebody is really kind of a very new to the Verilog, so if I ask you like what are the data types available in Verilog, I mean you don't have to really know everything, but at least the two important data types. Okay, so wire, it's called net, right? Okay, and the register, right? Okay, now I just kind of one important slide. Okay, I think I'll just move on. Yeah, so I have somewhere, yeah. Okay, so basically, right, so the net data type, okay, is the one, of course net is like a kind of a wire, maybe it connects output of one block to the input of one. Okay, and then so we have what is known as the reg data type. Okay, so this is where most of the students will confuse. Okay, now we also know a register from our digital design background. So this might be stands for a flip flop or something like that, right? But here in Verilog we have a data type called reg. Okay, we also call it as a register data type, but do not confuse this data type with the register in your digital design. It so happens that sometimes this register data type will exactly match the flip flop or a latch in your digital design, but it's not always. Okay, good. Sometimes the register can also be a wire. Is that clear? It's not necessary. Okay, so right, so I'll again repeat, it not necessary the reg data type in Verilog always synthesized to a latch or a flip flop, which we have understanding of, it will store one bit. In general we call it as a register, right? But it not always happens that okay, reg data type will synthesize to latch or a flip flop. It can also synthesize to a wire. So we'll look at these details later. Yeah, good. Okay, so one more thing. Okay, so before going to that, so this is where many of the students will confuse. Okay, as I said, right, so I am just picking up some kind of an important, let's say the aspects where the students will have confusion in the interest of time. Okay, so here, so what we are trying to really show is that there is something called port connection rules. Okay, suppose the idea is that, of course, I presume that everybody is aware of a module. Okay, right, now it's a module is similar to your class definition in C++. Of course, right, as such, if you define a class, there is no use, right. So we have to create an object out of it. So similarly, in module, let's say in Verilog, module is similar to the class, and we have to create an instance out of it. So that means we have to instantiate that block in some other, let's say kind of test bench or somewhere, if you wanted to really use it. Okay. So now, so most of the time, of course, let's say so you write, let's say one module, that itself is your top level module, and then maybe you wanted to really test it or something, right. So what you will do, you will take this module and instantiate in a test bench or something. Okay. So now when you instantiate it in a test bench, so what I will say that, okay, so there is a top level module which is driving the inputs of your this module. Okay, yes or no? Okay. Now what we are trying to really say is that there are some rules which you need to really follow, right, in such case. Now you might have really observed that, okay, when you are declaring a module, let's say, so did you kind of declare any time the inputs as a reg, right, never, right. So outputs could be a reg or a net. So that is what we are trying to really depict here, that so this is your inside the module, right. So maybe this is your test bench, you can think of, right. So that means whenever you declare a module, the module inputs cannot be reg, they have to be net, right. Okay, the idea is that, so if this is a kind of a module, you are trying to really connect it, right. If the input changes, so that has to really propagate it, right. It is not necessary that you have to save it, right. That is what the input means, right. Whatever it's connected to changes, that same changes it has to go propagate to inside the module. So that is the reason the module inputs always are kind of a net type, right. Depending upon the context, okay, this output of a module, right, could be a net or could be a reg, right. But now what that output connect to in your test bench, right. So what, see here, so you need to connect to that output and just see the changes, right. It's not like that you have to save it, right. So it's something like on a breadboard, you wanted to see one of the output, right. You just simply connect a wire and just check in the oscilloscope, right. So that means the output cannot be reg, right. So I mean the test bench output cannot be, let's say, reg, right. It's just a simply a wire, it's just you are watching the output, that's all. Okay, now what, let's say, driving the input. So now let's say there is a clock design or the counter design you have done, yeah, there is a counter design you have done. Okay, there is a clock input. Okay, how do you create a clock? So maybe use some kind of always block and you will say hash clock equal to not clock, right, something like that you do it. But now if you see, right, when you do that statement, you are assigning maybe in the clock to in the beginning to 0, right. This is a time t equal to 0, right. So at this time the clock equal to 0, but are you assigning the clock at t equal to 1, 2, 3, 4? No, right. You are just simply saying that not clock equal to not clock after 5 time units. But what is the clock value here? Here I mean t equal to 1, 2, 3, right. Okay. So that means the one which is driving the module inputs, in for instance a clock and all, they have to be declared as a reg. The reason is that you are assigning only once, right, and it has to save its value until the next assignment. So then it has to be reg type. And actually if you see, right, I mean there again there is always a confusion among the students, when should I declare something as a reg, right. You have this notion where you are assigning only once and until the next assignment it has to store the value. That time definitely you have to declare that as a reg data type, and again you see, right, that reg data type will synthesize to a wire or a latch or a, let's say, flip flop, that's different. But when you are modeling, let's say designs, when you have this notion, right, you are assigning a value once and then it has to store the value until the next assignment. In between you are not assigning. That time definitely you have to declare that data type as a reg. Is that clear? Okay. So always, you should have this picture in mind. What drives what? What should be the data type? Is that clear? Okay, good. Now, so let's go to the, I think already okay. So as I said, right, the most kind of the use statement, and of course in a data flow modeling, is this continuous assignment statement. So as the name says, right, the continuous assignment statement, and the other one which I said, you assign once, but it will it has to store until the next assignment. Okay, that is the reason we call whatever we declare in always block as a procedural assignment. The property of the procedural assignment is that on the left hand side variables, they must be reg type. So right, and then they will store the value until the next assignment. Okay, but whereas if you come to the continuous assignment statement, so of course, right, the syntax is something like this. We say assign, right. Why we say it's a continuous means, right. So this I1 and I2, they are evaluated every time, and then they are continuously driving this out. Okay. So that is the reason we generally we will not use the continuous, but actually so the proper name would be the continuous assignment statement. We will say simply assign statement, but actually so it's a continuous assignment statement. So idea is that the right hand side is kind of evaluated, it's expression that will the result of that will really drive the left hand side continuously, right. So now as I said, right, if it drives continuously, it cannot be reg type, it has to be net type. Is that clear? This is where most of the people struggle. So now once you know what is a continuous assignment statement and what is a the procedural assignment statement, everything should be clear. Yeah, okay, let's move on. So I think, right, so this expressions operand, it's something similar to what Steve spoke about. So I'll just skip in the interest of the time. Okay, fine. Okay, so we always have all these reduction, bitwise and operators. Good. Okay. So now, okay. So in a behavior modeling, this is where the procedural blocks comes into picture, and as I said, right, there are two procedural blocks. We have initial and always. So initial, we will only use it in the test benches, and of course, so always, right, we can also use it in test benches to generate the clock and all, but in a real synthesized designs, so always block is used. Okay, good. So here, okay, so this is what kind of that clock design is, right. So fine, okay. So okay, so again, right, so one of the kind of a common question is that there are like two types of assignments in procedural blocks, what is known as blocking and non-block. You might have heard, right. Okay, so what exactly the difference between these two? So what we will do is that we will look at these with few examples. Okay, so here, okay, I think I don't have to really repeat, I guess, the always syntax, I guess, but if you doesn't know, maybe I'll just reiterate. So we have this always block, and then we have this @ symbol, okay, and then so we will give the list of signals and we call it as sensitivity list. The idea is that whenever any one of them change, so we can also put a comma, A comma B comma C, or A or B or C, doesn't matter, it's a different way of writing the code. So the idea is that A, B, C changes, okay, A or B or C changes, so we have to execute this whole block. Now if somebody is not changing, what will happen to the statement? What will happen to the statement? It has to hold its value, right. So it has to hold its value means it's a reg data type. That means in a always block, whatever you find it on the left hand side, they have to be reg type, but in a continuous assignment statement, the left hand side will be wire. That you should always remember. Okay. Good. Now in this case, okay, so the blocking assignments are represented using an equal sign, and later on we will see the non-blocking. So it's a less than equal to. Okay. So here what we have is that, okay, some two statements n1 equal to so there is a XOR symbol A XOR B, and S equal to n1 again XOR C. So the idea here is that, so when you say it's a blocking statement, so when you see this blocking assignments, the first statements block the execution of the second. Okay. So that's the reason we will say it's a blocking. The idea here is that, so now we are kind of calculating the value of n1, right. So now the calculated value will be used in the next statement. Okay. Here, so we have A XOR B, right. Okay. So now that calculated value, new value, is really used as, in the next statement, right, at that time. Okay. So I mean, that's the reason we say it's a kind of a second statement is being blocked by the first statement. Until I complete the first statement, I will not go to the second. Okay. Is that clear? Okay. Now let's look at this one particular example. So just think about this circuit. Okay, of course, right, there should be some kind of a space here after the passage, kind of copy paste mistake, but yeah, so there is a code, so always at the passage of a clock, so right, and then we have this true statement. Okay. Now actually, so my intention was I wanted to kind of swap the lower byte with the higher byte and higher byte with the lower byte. Okay. I wrote two always blocks. So think about 1 or 2 minutes and tell me what is the answer. What will happen? So my intention is I wanted to really swap the lower byte with the higher byte and higher byte with the lower byte in this word. Okay. The reason why, I mean, okay, now you tell me what will be stored in 15.8 and word 7.0. Okay. Now these two always statements are in the same file. Okay. So what will happen? It can run, right? I mean, again you see, right. So now we have, right. I mean, this is where also kind of again the people who have a background in the sequential logic have a problem in thinking in Verilog. If you see, right, each always block, it's a parallel activity flow, right. It's independent of the other always block. Now in your answer you are thinking that the first one will execute first, right. So what is the guarantee that the second one also could execute first, right? I mean, you see, right, I don't know how does the compiler results, right. It could happen that the both lower byte and higher byte could also have a lower byte or higher byte. It's unpredictable. Yeah, right. So now here, I mean, that's what the problem we have. Okay, it's not predictable. So we'll see the latest solution later, but that's what the issue with this code. Okay. So now, okay. So here, the same code. So what we are trying to really do is that we are trying to use the blocking assignment. So non-blocking assignment. Okay. The non-blocking assignments are kind of represented with less than or equal to symbol. So here the idea is that at the passage of the clock, right, and again since these are non-blocking statement, that means both of these statements are executing in parallel. So what you are trying to do is that, okay, you are trying to really execute these two statements, you are trying to really read the word 7.0, 7:0, yeah, and then you are trying to read the higher byte. Okay. So the assignment is not happening, you are just trying to really read them, yeah, you are trying to really read them, but the assignment not happening. So now let's assume that there are the temporary variables t1 and t2, right. So this word 7 dot, let's say lower byte is stored in t1 and the higher byte is stored in t2, right. So both you are reading, right. So the reading is happening at a reading, or of course in this case simply reading, right? Of course, if there is some expression, right? So we will evaluate the complete expression, right? So that expression evaluation is happening, and then I'll store some, think of, we are storing, let's say, temporarily somewhere in T1 and T2, right? Now at the passage of the clock, right? So the assignment happens. Okay, now we have the value stored in T1 and the T2, right? So we can perfectly swap, right? So that's a, kind of a solution for the problem. Yeah. Okay, now, so just to again, get used to this. So here again, think about this block. So draw yourself on a piece of paper what comes out of, let's say, these, let's say, code. So I will tell you later on. So whenever you see the passage of the clock, right, left hand side variables, in the, right, the code has to get a flip flop. I mean, I don't know, there are some exceptions, but the most of the time, to be on safer side on record. Yeah. Okay, now that means you can think of, right. So the B and F are going to be flip flops. Okay, now what gets connected to what? So try to draw the circuit on your own. So take a minute or two and try to draw the circuit on your own. I'll just check the live. Okay, so if you think that if you have different answers, so maybe let me explain. Okay, so here at the passage of the clock, right, what you are trying to really do? You are trying to really read A and read B. But now, if you look at here, right, you are trying to really assign B, right, here in the first statement. And you see, right, the assignment is happening at a different time step and the expression evaluation is happening at a different time step, right. So now, if you think that these are the blocking statement, then you will say that, okay, oh, this C, it is the same B, right, but no, I am trying to really calculate the new value of B and then I am trying to really read the old value of, let's say, B. So that, and again as I said, right, the passage of the clock, the left hand side variable has to be flip flops. So now this is the kind of a B flip flop, right. So this output is B. I am trying to really read the value of this, right. This is my F, okay, and what is, let's say, B. So I am trying to read the value of A, and then of course, right. So in a passage of the clock we have, so the clock will get connected to the clock pins of your D flip flops. Okay, now the same, I think somewhere I have, I guess. Okay, so this is what a kind of a swap thing we have seen. So I'll just skip. Okay, so now I think, with this example also we can really see the difference between the blocking and non-blocking. Okay, so now for this example, what is the difference between a, let's say, synthesized, let's say, circuit for the blocking and a non-blocking? The question is, so you are seeing, let's say, two descriptions, right, one with the blocking and another with the non-blocking. So what is your answer with respect to synthesized diagram of a blocking and synthesized diagram of a non-blocking? So the answer is that the both are going to be same. The reason here is that it's not like that, okay. So for instance, if you look at maybe the left hand side variables, right. So now something y we are calculating here, okay, the y is not really getting used in the next, let's say, any of the statements, it's like independent. So now the idea is that, so whenever we call this as a, of course, now in the previous code, right. So here, I mean, let's assume that if it is a blocking, we will see later. So now we are trying to calculate the new value here, and if it is a blocking, we are trying to really use here. Whenever there is a signal interdependency, the blocking and non-blocking will differ. But in this example, as is shown, right. So there is nothing like, you are calculating the y, you are not using anywhere in the next lines, right. So whether it's a blocking or non-blocking, the circuit should be really the same. Okay, good. So whenever you have the signal interdependency, it will change. Okay, so that's what we have here. Okay, good. So here, right. So, the signal dependency is there, right. So, the logic will really differ. Okay, good. Now, okay, so let us look at, okay, okay, what here, this slide, yeah, okay, I'll come to that, yeah, good. So, let me explain you this one and then I'll come back, okay. Right. So, here, so what we are trying to really show here is it, okay, so if you look at here, right, so what are your primary inputs, A, B, C, right, okay, and you are trying to calculate the value of N1 first, okay, and then, so, and try to calculate the value of S, okay. Now, in a blocking statements, okay, so your semantic says that you have to use the updated value of N1, yes or no, okay, but now in a non-blocking statements, okay, so you have to use the previous value, okay, that is what you will be able to see here, okay. So, these are your ABC, so these are your ABC, yeah, okay, and then, so you have to calculate N1, right. So, N1 is nothing but XR, right, okay. So, 0 0, it is a 0 here, right, okay, XR of what, A and B, right, 0 0 0, 0 0 0 and 0 1 1, 0 1 1, right, 1 0 1 again, 1 0 1, 1 1 0 and 0, right, okay. Now, to calculate the S, now if you look at these two, let us say, diagrams, as far as the N1 is concerned, there should not be any difference, that is the reason the N1 signal really matches in both of them. But now, when it comes to the calculation of S, okay, there is a difference, right. So, what you do is that you should really use the updated value of N1, right. So, what is the updated value? So, this new value of N1 you will use, and again what is the equation, N1 XR C, right. So, you will see 0 0 0 1 0, right, 1 0 1 1 1 again 1, it is 0 0 1 1 1 1 0, yeah, and 0 0 0, yeah, and 1 0 again 1. But now, whereas here you have to use the previous value, right, okay, right. So, now let us look at, you are trying to calculate the value here. So, what you will do, you use the current value of C and the previous value of N1, right. So, here, right, 0 and 0, it is a 0, right, okay, and then 1 and 1, it is a 0, okay, 0 and let us say 1, it is a 1, yeah, 1 and 1, it is a 0, 1 and 0, it is a 1, so 0 and 1, it is a 1, right. So, you are using the previous value of N1, yes or no, right, that is what the semantics is, okay. So, now Answer asked one interesting question, right. This is what exactly happens in the simulation, okay. So, Answer is talking about why the circuits will differ. Anyone want to answer? Huh? The statements are different, but actually this is one of the kind of, I think Answer observation is correct. The circuits will not differ, they will be exactly the same, but what will happen is that the same circuit also gives after synthesis the same result as the first one, right. So, then what exactly you mean, right? You have a different behavior in a simulation, but after synthesis you have a behavior with respect to which is equivalent to blocking. Now, what we have? We have a synthesis and simulation mismatch, yes or no? I mean to say that, so both will, let us say, will synthesize to the same logic. I will also come to the reason why it will synthesize, but now with respect to the first one, before synthesis in a simulation it is giving the expected result, after synthesis also it is giving expected result, but the second circuit in synthesis it will give the same result as the first one, the blocking one, but in a simulation it will give the result just now we have seen. What is the reason? So, basically, I mean, now in hardware what we have? We have a latch and we have a flip flop and all, right. So now if I ask you this question, in this during this always block, with this always block, can we get a latch? Okay, the answer is no. So we'll also see when we get a latch, right? So now here, if you wanted to really have a right behavior, what you should do here is that you should have N1 in here. Okay. So now in your sensitivity list, you should also change N1, right? So then it will kind of trigger immediately the logic. I mean, right? So now you will have the same kind of let's say output as expected. So there is also one more example, so which I will show you, which really kind of explains in a different way. Okay. Good. So basically the the one point I wanted to highlight is that there is a synthesis and simulation mismatch. We should not have that. Okay. Good. Okay. Now I mean, this respect to the first example you have seen. So we have drawn kind of a two, let's say, flip flop. So one flip flop output is going to the other one. If you look at maybe the first circuit, right? So we'll have exactly the same signal, right? So they are kind of a parallel. Now we see, right? So B is also kind of a, right? F is also A, because you are trying to really use the value of updated value of B. So that's the reason F is also connected to A, yeah, and B is also connected to A. But whereas here, so we are reading the old value of B and we are calculating the new value of B, right? So that's the reason, right? So B old value you are reading and calculating the new value, right? It should be clear now. Okay, good, fine. Okay, and again you see, right? So I think one of the Steve's explanation, kind of explanations, right? So he was really trying to use only the ternary operator, right? So the ternary operator is nothing but your maybe, right? So colon and all, right? So conditional operator, and this is equivalent to our if else, and now we have a case and all those things, right? It's nothing but it's a nested if else, and everything will really kind of maybe will boils down to those multiplexer implementations. Okay, it's clear so far? Okay, good. I think so. So here, okay, I just wanted to kind of highlight few things. Okay, I mean generally, right? So we should really know how to model a flip flop and how to model a latch. So this is a kind of a flip flop code. Okay, so here what we have, this passage of the clock. I mean in general, right? So whenever you have a passage in your always block, right? Maybe the left hand side variables will synthesize to the flip flop. Okay, good. So now here, of course, so I mean the Q and all, so maybe could synthesize to flip flop. Okay. So now what we are saying that if not reset, right? If the reset is kind of a 0, right? So right, reset equal to 0, not reset will become 1. That means if condition is true, right? So we say a Q equal to 1 tick B is 0. Okay. So that means we wanted to really reset the flip flop, and I can say it's a active low reset. Yeah, and now else Q equal to data, right? So it's something like this here, right? So now if I ask you this question, right? So this is a clock pin. The clock pin is connected to CLK signal, D is right, I mean connected to data, and the Q is connected to Q. Right? So now if I ask you whether it's a synchronous reset or asynchronous reset, how do you really understand that? Is it a synchronous reset or asynchronous reset? So why do you say? Right, if you see, right, that's why you should look at it. So at the passage of the clock only you are evaluating, so where you are looking the reset signal. When the passage of the clock comes, then only you are going inside the block and then you are looking at what is the value of reset. That means reset is being looked at with respect to clock signal, synchronous, right? Asynchronous means what we should do? We simply write or, I mean in this case, right, so since I have an active low, I will say it's a negates resets, negates reset, yeah, alright, that's all. So that is asynchronous synchronous. Okay, good. That's what I have. Okay, now I think somewhere I should also have a D latch, maybe. Okay, if not, so there might be somewhere else, we'll see. Okay, I'll just skip some of these blocks. Okay, so and again I'll just talk about one of the aspect of you know, coding, you know, the sequential circuits. Okay, good. Yeah, this is what we have. Okay, so we're talking about the latch, right? So again, look at the code. Okay, so now whenever we talk about a latch, right? Again, you know, think about your D latch, right? So SR and all there, but you know, so D is the most one, right? So now for a, let's say, D latch, what is the important condition? We have to really know what is the enable pin, right? Right? Yeah. So whenever the enable is there, the input is really captured to the output, otherwise it just have the same value. Okay, now if you look at this code, right, so do we have a passage of the clock, right? So that means there is no question of having a some kind of a flip flop or something. I mean, you know, I am just trying to really kind of, you know, put together the thoughts, right? So when we have a passage of the clock or the negate of the clock, we will get, you know, maybe flip flops. So now always at the rate we do not have any passage or negates, so that option is ruled out. Okay. Now what we are saying that always at the rate C changes or D changes. Okay, then this block should be executed. And now what we are saying, if C equal to 1, if C equal to 1, so maybe Q equal to D, else we are not saying anything, right? So that means, right, we can think of, right, if C, right, this is like enable, right, if the C equal to 1, then only we will copy, otherwise we have to hold the value. Now this is giving a notion that, okay, that Q, if you look at, right, in one of the condition, right, if condition is assigned, else condition is not assigned, right. So that means whenever you have this always at the rate without any passage and all, the sensitivity list, we can get a combination circuit, we can get a latch, but we never get flip flop, right. Now when do we get a, let's say, latch? We have this incomplete assignment, we are assigning the signal on if, but we are not assigning an else. So now this is giving you notes that else means store, I mean keep the same value, right. So that is where the latch comes. Is it easy now? Right. So I will repeat, whenever we have a passage of the clock or negate of the clock, we should think about flip flops, right. So there is nothing like here, right. So that means there should be a combination logic or a kind of a latch. The combination logic will appear when the left hand side variable is assigned in all possible conditions. Now if you see here, if C equal to 1 you are assigning, and right, if C equal to 0 you are not saying anything. So that means your intention is that C equal to 0 means hold on, it is a latch. Is that clear? I mean, you know, I think this will help you a lot. I think, you know, again this is D flip flop code. Okay, now so this is a D flip flop with a asynchronous reset, so which we have looked at, so I will not repeat. And now, I mean, okay, this I think, you know, I think the issue with the, okay, so Wi-Fi is gone. Yeah, I think should be better now. Yeah, okay, at least good. Yeah, now, okay, now this is a D flip flop with asynchronous reset and a preset signal. Okay, now let us spend some time on this one. Okay, now as I said, right, so I think in the other class, so whenever we have this always statement and then we have this now passage, negates and all, right. I mean, now in the signal name somebody written as a clock, somebody is written as a reset, right, and somebody, you know, kind of, you know, written as a preset. So do not go by any other names, but in this case, right, clock might be a clock, right, first case, right. Generally we wanted to use a meaningful names, right. So reset could be a reset and the preset could be a preset signal. I mean, sometimes the reset and clear, you know, both are the same, right. So here, I mean, in this case I think it exactly matches, but we should really follow kind of a structure, how to really decide which is the, you know, going to the clock and all. So that I will explain, right. So now if you see here in this part of the code, right, I mean whatever the signals, right, we have if not reset, that means, so again, you know, there is a kind of a precedency, right, precedence, yeah. So now we are giving a lot of importance to, or maybe the first signal that are not reset. That means, again if you see, right, so whether it's a synchronous or asynchronous, whatever we should say, you are getting into the block when any of the signals are changing, right. So that means it's asynchronous signal, right. So now if not reset, what we are trying to do, we are trying to set the Q bit to 0, right. Now else we are saying, right, else if, right. So now the second priority we are giving to preset. If the reset, first we should really set the Q output to 0, and if it's a preset, it's a active low preset, right. So that's the reason we have these bubbles here, right. So that means we should supply 0, then only it will be reset or let us say preset, right. So now the second priority is given to the preset, so we are setting the output to 1. Now else we are saying, right. So here passage of the, let us say reset we said, the negation of the reset we said, and the negation of preset we said, and else we are saying what is left out, clock, no, yes. So now, so how do we really determine the clock is something like this. The rest two are used. Now if instead of this preset I will call as A, this I will call as a B, and now I will call this as a C. Now A, B, C, right, it does not make any sense. I do not know which is a clock, which is a preset, which is a reset, right. Now I have to really look at the code, okay. So this B is used here, okay. So here A is used, okay. What is left out? Else, right. So that means this part of the block will trigger when both are not there. That should be a clock. Is that clear? Of course, right. So we will not write like this ABC code, but if somebody writes, wanted to check your understanding, you should know it, okay. So this else block only will trigger when the passage of the clock is there. That should be right. So passage of the clock, right. So Q equal to D and this one. And again you remember, always when you have the statements with respect to passage, negate, clock, so you are modeling a sequential logic, use only non-blocking, right. It's continuous assignment statement, always without any passage or anything, right. So use maybe the combination logic, use only blocking, okay. So here, so this is a flip flop with enable signal, the same explanation here, but now else came, right. So we wanted to execute this block, but we have else if, right. Now can you tell me where you are checking the enable, with respect to the clock or without respect to the clock, right. It's a synchronous enable, right. I mean you see, right, the passage of the clock only this will execute, and at the passage of the clock you are looking at the signal enable, right. So this could be your enable, and it's a flip flop with a preset, reset, and with enable pin. And now you see, right, these are the typical things which we always use, and okay, good, okay. So now I mean so this I included because of Biswajit. Last time we had issues with modeling this sequential circuits, okay. I think it will not take much time. So I mean, what kind of sequential machines we have? Only two types, right. What are those? Mealy and Moore, right. So what is the difference? Okay, right. So Moore, I think it just output depends upon your state, and melee is, okay. So there is always, right, if you design anything, right, so there is always one cycle delay or whatever happens. So here now I mean with this example what we will see, right, once you know the kind of a state diagram, I mean of course, right, anyway we wanted to do with a pen and paper, your circuit synthesis and all, you need to have a state diagram, right. So given any problem specification, you need to really come up with a state diagram, right, and after that of course you try to synthesize with your D flip flop or T or JK or whatever, right, but of course, so we can also really write the code. So here in this, let's say example, I think I just copied from this Lameri's book, and if somebody is really interested, right, wanted to really learn the digital design and all, I mean especially with the Verilog, that's one of the finest books you can find, it's a kind of very lucid explanation, and he also has all his kind of video lectures, everything online, yeah. So I think he works at University of Montana, I guess. You can just search for him, and of course so I have the book name in the, let's say in the reference slides. Okay, let's come back here. Okay, here, so in this example, we wanted to design a kind of a push button window controller. Okay, so somebody is giving a kind of a specification here. So this window controller will send the appropriate control signal to a motor to open or close it whenever the button is pressed. Okay, the system must keep track whether the window is open or let's say closed in order to send the correct signal. I mean, you see, right? So if it's open, maybe it should close, right? You should not try to again open it, right? And if it's closed, right, and then it should open it. Okay, that's what it means. So thus a state machine is needed. So the block diagram is given. Okay, so there is a kind of a button. It's a push button, yeah. So right, so of course, right, you know the difference between a push button and a normal switch, right? So the push button, once you press, it gives a pulse and come back, and we have the switches on maybe on the basis 3 board. So as long as it's, let's say, in other position 0 and 1, it's continuously it gives 1. The push button, but it will come back. Okay, so now that's what we are giving this, this push button window controller, and we are envisioning that, okay, there are 2 signals as output signal, open and a close, and now the motor we have to really kind of rotate in one of the directions. For open clockwise and the close counterclockwise, right? Okay, good. So now I mean we are again coming up with a some kind of a state diagram. Let's say there are 2 states. It could be in a closed or open. Okay, let's say we are in closed state. Okay, in a closed state, I mean nobody is pressing the button, so we can say it's a press equal to 0. We have to be in the same state, yes or no? That's the arrow is shown, and then of course, right, we don't have to do anything, right? Right. So that means open is also 0 and close is also 0. These are 2 signals, output signal. Okay, now if we are in a closed state, somebody press a button. So we have to go to right open state. Okay, and then right what should be the signals? Open should be 1, close should be 0. Okay, again maybe it could be in the open state. So nobody is pressing any button. So press equal to 0, both signals should be 0, and then so again if you are in open state, somebody press a button, you will come to the closed state. Okay, and of course this time open should be 0 and close should be 1. As simple, right? Right. So once you have this state diagram, right, it can be really kind of a modeled easily, and of course, right, the I mean the method which we are going to discuss, right, it doesn't matter whether you have 2 states, more states, it will be the same. Yes. Okay, good. So here I mean how do we really start? Of course you start with a module definition, output reg, open CFW, close CFW, CCW, yeah, and we have a clock and reset and the one input press, right? Okay, good. So here, okay, now when you are modeling the kind of the state machines, okay, so 2 things you should remember, right? You should really calculate the next state. So next state is a function of input and present state, right? Let's assume that, but what is the next state logic? I mean, okay, so maybe if possible we'll try to. So how do you really draw kind of a simple state machine, the block diagram or whatever, right? So we have some kind of a flip flops, right? Yes, and then multiple of them are there, right? So what you do is that you read their current state and you calculate your next state, right? Yes, and then you try to update the flip flops, right? Okay, of course for the next states we also can give calculating the next state, inputs also will be there, right? So now the calculation of the next state really depends upon inputs also, right? And now in a Mealy machine what will happen? Your outputs, now we calculate the next state, right? So we need to calculate the outputs, right? So now if you wanted to calculate the output in Mealy machine, output is a function of right the present state and the input, right? So of course in Moore machine output is only state, and of course this will not be there. The same thing we have to really do it. That's what I want to say, right? So now when we are really kind of modeling the sequential thing, okay, right? So we need to really come up with what is known as next state logic. Now the next state logic, the way we have drawn the diagram, right, it's a pure combination logic. We will read the current state values and the input and we will try to calculate the next state, and then whenever the positive edge of the clock comes or negative edge of the clock comes, we will simply assign. Yes or no? There is nothing really great in it actually, right. Let us assume that, so here in always in your sequential, let us say code whatever, right, you will always have what is known as this next state memory block. This is where you calculate the next state and at the passage of the clock you just transfer to the current state. Okay, here what we are trying to really say that, okay, so we have always at the passage of the clock or the negative of the reset, of course, right. So we can assume, right, one of the state is you enter when you reset, press a reset. So we are saying that, okay, it's a active low reset and then asynchronous reset. So you always start with a kind of a, let us say, closed one. Okay, that means whenever you press, you start with a closed state. Okay, that's what we have. Okay, that means, so in the previous diagram, if I wanted to say, if it is not reset, so we are here. Okay, it's clear. Now, when the reset is not there, what we should do? What is your current state? Okay, what is the current state? Next state will come, but what is the next? Let's say current state. You might have really calculated the next state already, right, based on the present input and the current state. You just at the passage of the clock, you just transfer it. That's what it's saying, right. So somewhere we calculated, let's see where we calculated this next state, and then at the passage of the clock, simply we are transferring. Now you see, right, any whether the states are 2, 3, right, something similar you find it in all the sequential machine codes. There is nothing much difference. You always calculate the next state at the passage of the clock or negative of the clock, you just transfer. This block really looks almost in same in all sequential machines. Right, so we call it a state memory block, and this is only the kind of the flip flop or the sequential block. The rest are all combination blocks. Right, the way we drawn, right. So the next state logic, read the current state, read the inputs, calculate the output. That's all, right. And again the next state logic, right, read the input, read the current state and calculate the next state and keep it ready so that you can assign at the next position. Okay, here and most of the time, so we will have what is known as 2 resistors. So why we have to really have a resistors? Because in always block we are going to use, so it's a current state and a next state. Okay, in this case the current state and next state, the 2 kind of variables we are using, right. Yeah, so that will represent one of your state, right. The current state could be open, current state could be closed, and the next state also could be open or next state could be also closed. And again you see, right, so we can also say that, okay, I mean we can also really define 2 parameters. So one for closed and one for, let's say, open. So they are like defined as a 1 tick B0 and 1 tick. Suppose if you have 4 state, right, we will have a 0 0 1 0 and 1 1. Is that clear? Okay. Now as I said, right, the next state logic we have to calculate, right. The next state really depends upon only the present state and next state. Now if you see, right, when I am coding this next state logic, always let's say blocking, right, but if you look at this one, we have non-blocking. As I said, sequential thing non-blocking, combinational blocking. Okay, good. So here again you see, right, so what does the next state really depends upon? As I said, it's based on the current state or inputs. You just list all these signals in your always block, right. Okay, now you are checking the case, right. If you are in the closed state, okay, if the press equal to 1, what should happen? You should go to the open state. So right, your next state will become open, and else you are in the same state. Okay, again if you are in the open state, if somebody press a 1, you will go to the closed state, else you are in the same state. And of course, right, we have a default which is just a next closed state. Okay, so this is your next state logic, it's a pure combination. So similarly, okay, the output logic, right, output logic depends upon your again inputs and the current state. Again if you see, right, so the case statement we are depending upon the current state. If you are in closed state, if the press equal to 1, right? You should really open it, and the close of course will be 0, else both are 0. And if you are in open state, if somebody press, right, so open should be 0, open should be 0 and the close should be 1, okay, else both are 0, and we are saying the default is 0 0, that's all. Now only thing which kind of a change in Moore machine is we will not have inputs, that's all, right. Now you see, right, once you know the Mealy machine and Moore machine, right, and coding the sequential machine is very simple, and there is no other better way to code than this one, and it is easy to understand and simple, okay, good, fine, okay. I just wanted to mention that. And you see, like, so sometimes we have to really kind of write counter designs and all, right. For the counter, we don't have to really write the state diagram and all, but simply we can really model with a behavioral statement. So here if you see, we have this positive of clock or negative of reset, okay, and if reset we are saying the counter value equal to 0, else count equal to count plus 1, that's all, right, it just counts, okay. And again you see, right, it's a, I mean, of course, it's once it reaches the 15, it's again rolls back to 0. And now if you wanted to really kind of check, maybe it's a mod 10 counter only, right. So what we can do is that, okay, we can check if count reached a 10 value, of course reset means it's a 0, else first you check, right, if the count already reached 10, you initialize to again 0, right, else you just count equal to count plus 1. So but of course this should come first, okay, but if you do it again, then the results will be changing, okay. So here, okay, and we have a counter with enable pin here. So if you see here, if the reset equal to reset is active, the count equal to 0, but now you will not count simply, right. It's not like every clock cycle you are counting. Whenever the clocks, right, whenever at the clock heads, if you have a active enable signal, then only you will count. So in the previous one, here every passage of the clock, I mean in the passage of the clock you are counting, but here in this one, right, whenever this enable is there, then only you will count, okay, that's a difference. And again you see, right, so we can also have a counter with a kind of a load also. So if enable, this should work, and of course, right, so now if the load signal is active, we wanted to load a kind of a predetermined value, otherwise so count equal to count plus 1, okay. I mean these are the typical, this, I mean you will enter, okay, good. So now this design, I mean, so one of the kind of a common task is that you have to model a register, and again you see, right, this is always kind of a confusion, right. Register could be 1 bit, right, again in the context, when we talk about the processor and all, at least we will talk about 8 bit or 16 bit or 30 bit registers. So again you see, right, whenever we talk about register, so the D flip flop code should come into mind. Now if you look at here, right, it's exactly the code of D flip flop, right. The only thing is that here we have 8 of them, right. I mean you see, right, so we have the vector, I mean, right, so it could be 16 also, or 15 also, right, 0 to 15 is a 16 bit register, right. But now if you look at only this part of the code, it's exactly your flip flop code, but of course, right, here ridge out and maybe ridge in are 8 bit vectors, right. So basically it's a flip flop, okay, good. Yeah, I think that's what should be fine. And again, as I said, right, so this was a book I was really referring to, and if somebody is really interested, as I said, right, so he has all his lectures online. I'll just pass on the kind of a slides if needed. So and the lot of kind of a programming examples and all, so somebody can really look at it, okay. So far maybe I just try to give a kind of some glimpse of the Verilog itself, and kind of a common misconceptions or misunderstanding, okay, good. How do we really understand such nitty-gritties? So what we will do now, I mean writing the code is one part, right, and this is where it's kind of there are a lot of not much material available, and again as I said, so we'll also kind of formulate some rules by which we can really understand easily, okay, good. So again so we call it synthesis. So what is the synthesis general meaning, right, general English meaning, right. So transforming from one form to the other, right. So now in a Verilog, let's say domain, right, we have statements. So now after synthesis, what we have to get? We have to get some kind of a flip flop, latches and all those things, right. So now of course there are some tools which does that. So we are, let's say, transforming from one form to the other. Now, so of course, right, the synthesis really depends upon whether it's a ASIC synthesis or FPGA synthesis, right. Okay. So now, I mean, in FPGA synthesis, in FPGA what we have, LUTs and all, right. So maybe your synthesized netlist only consists of your LUTs, but in ASIC synthesis we will have AND gates, OR gate, multiplexer, and again depends upon what you have in the library. It's not necessary that, if you think of a full adder, right, in my library I have 1-bit full adder, I don't need anything, I'll just simply instantiate that 1-bit full adder. But if I do not have a full adder, I have a half adder, I will build the full adder using 2 half adders. Suppose in my library I don't have 2 half adder circuit, what I have to do is that I have to build my half adders using maybe XOR gates. Okay, let's assume that again XOR gates are not available in my library, I have only simple AND gates, OR gates, right. Even the XOR gates tries to be built using that components. Again you really see, right, the synthesis really output depends upon what you give as an input, right. If you give input with respect to the standard library, right. So standard cell library you will give, and it all depends upon what the standard cell library contain, the output. If you have all the gates, like generally we see, right, the multiplexers. So generally the multiplexer also will be given as a simple kind of a standard cell. So whenever we need a multiplexer, we will not implement with inverters, AND gate and OR gate, we simply use the multiplexer. It's much more efficient in terms of area and all. Okay, good. So maybe after this let's say statement we will take a break. Okay. So now I am just trying to ask myself, what are the kind of a value holders for hardware modeling in Verilog, right. So now here in a Verilog, or of course in the hardware, right, of course in the Verilog world what I have is a net and reg predominantly, right. But in a real hardware world what I have a wire, I have a flip flop and a latch, right. Now the question is, whatever you write in Verilog, that should really come and match to any of the things. Now I am making one statement that here a variable in Verilog HDL can be either of net or net type or reg type, right. So that means these two has to really map to these things. Now in the last statement what I am trying to say, that if there is a net data type, definitely it will become a wire. Whatever is very simple, a net data type has to become a wire. But now the reg data type, depending on the context, okay, it can become a wire, it can become a latch, it can become a flop. So just to conclude maybe this slide, in hardware we have a net, we have a latch and a flip flop, but on the Verilog side we have only net and reg. That means these two variables has to really map to these things, and the statement what I am saying, that if it is a net, it becomes net only, it is a wire. But if it is reg, could become also net, reg could also become a latch, reg could also become a flip flop, and then we will look at following lectures, right, what are the conditions or in which conditions it will happen. Okay, good. So here, so let's look at this part of the code again. From now onwards we will just look at the code and think about what comes out. That's the idea, right. So let's look at this part of the code. Okay, so now we have always block, right. There's nothing like passage or anything, right. So only option at the latch or these things, right. But again latch means, as I said, right, if something should be there, that is also not there. Huh? Check. Huh? Okay, should be fine. Okay, so here, so the importance of this example is that, so here we have this TRQ, right, and of course we have a blocking statement and all, but now this TRQ is really used here. Okay, now if you think that, as I said, all the left hand side variables, of course, right, in a always block has to be reg type, but now if you say this SQP or TRQ, right, so they will both really kind of become a reg type, and now the circuit will something look like this TRQ, right. So now we see, right, there is nothing like a kind of a register or something came out. So again, as I said, right, if you are comfortable with the always block for even modeling the combination logic, use only always block, and of course, right, in always block we have this advanced constructs, right, if, else, case and all, it makes much more sense. and otherwise now we have to use only the ternary operators and the continuous assignment statement for modeling the combination. Right, good. So now again think about this circuit, and again this points to what answer Riley pointed out earlier. It's a blocking, right? So now you are reading TRQ even before you calculate. So what is the value of TRQ I should use? Maybe the past value, right? Okay, now the past value means I should either it should come from a flip flop or a latch, right? Is there any question of coming a flip flop here? Yes or no? No, right? Because we don't have any pass edge or any gates. So there could be a latch. But again, you wanted to assign the TRQ, right? The TRQ could be a latch. But again, latch means there should be some enable condition, right? And that means that the TRQ should be assigned in one of the if condition, else condition would have been kind of left out. It's not the case, right? Okay, this is again result in a kind of a synthesis and simulation mismatch. It should be some kind of a TRQ here should be added, otherwise it will not work. Yeah. So now you wanted to have it, and now if that is the case, so I think the previous circuit I think should also be the same. So the behavior will be the same. Yeah, that is the reason we should be a bit careful. We should not have synthesis and simulation mismatch. Yeah. Good. Okay. Now, so work out on this example on a pen and paper based on what we discussed. I mean, just you don't have to write the code or anything. Just look at the code and try to draw the diagram. Later on, I will pass on the thing to you. So, is there a question of flip flop or something? No, right? Okay. Now, is there any question of let's say latch? Yes, right? Okay. So, what is going to be latch? Again, you see, this is where okay. Let's assume this is your D flip flop, na? So, this is a D input, this is a Q input, and this is enable pin. Synthesis means what? We have to come up with a D logic. What should be connected to D? What should be connected to enable? What should be connected to Q, right? Okay. Now, in this case, right, what should be connected to D? What should be connected to enable? Think in this way, right? What should be connected to enable? If not SAT, right? Right, I mean, of course, so I will say it's a something like this, right? If this is true, this is a SAT signal, then only it will work, and then in that case, where should I really write Fox? I mean, doesn't make sense Fox and AND, but that's what the book has. Yeah. Anyways, where should I write Fox and where should I write AND? Very good, right? So this is your output, right? And this is input. Okay, and then there is something called S out, right? Where I should write. I mean, of course, if you have a Q bar, either way, of course, you can also take something like this, yeah, and then this is your S out. Yeah, if the Q bar is available, just take it from there. Yeah, of course, it's overlap with the other one. Okay, good. Yeah. Okay, fine. Okay. So now again, so when we have the continuous assignment statement, right? So here, if you see, right, this assign, this kind of a start out equal to the start in. Yeah. So basically, right. So always remember, whether it's always or the continuous block, we have to evaluate the right hand side. Okay. In the right hand side, we have an expression. In this case, the expression could be simple. Right? It's a not start in, right? That has to go to the left side. And again, as I said, right, whenever you have this continuous assignment statement, the start out should be really wire, and of course, right. So it should be really driven by whatever the expression you have. It's a not side. Okay. Good. Now, when it comes to the procedural assignment side, we had a blocking and non-blocking. So we talked enough. So what you do is that let's look at some examples. Maybe first I'll come here and then we'll go back. Okay. Think about this circuit. So draw me what comes out. So draw me the circuit, what comes out of this one. So maybe in this interest of time, I mean it's very simple. So of course here, if you see here, always there's a non-blocking, right? Of course, I mean you don't get confused. There's nothing as a positive clock or anything is there. There's no flip flop, right? And there's only one statement. It doesn't matter whether it's a blocking or non-blocking, but I would say that if it is combination, use only this one. Okay? So now, as I said, so there's no flip flop, there's no latch also. It's a simple reg A and reg mask. We should really AND, but since reg A and mask are, let's say 4 bit, and we'll get maybe 4 AND gates, right? Right? Good. Now think about this circuit. This one will be flip flop, right? Okay. Now whenever I say it's a flip flop, again what are the inputs we have? We have a D input, we have a clock input, and we have Q output. Now what should get connected to what? Very good. Okay, very good, right? So it something like this, right? So D flip flop. So the clock is connected to, of course, this CLK signal, right? And of course, right, each bit is connected to, of course, this reg A3 mask 3, right? Of course, for each bit we have one flip flop, right? So we have 4 bits, we have a 4 flip flop. Agreed? Okay. Now, so the other one which I said right here. Okay. So look at this, let's say circuit, and again you see, right, what we need to know is out only simple, kind of a Boolean minimization, and we need to know only the Karnaugh maps or whatever, nothing else we need. Okay, we'll see that. Okay. So look at this circuit. So what this circuit is trying to do, I mean whenever there is a change in preset changes, so count equal to preset plus 1. So basically it's an adder, right? Yes or no? But now there is one difference. Of course we can say it's incremental, and now instead of preset plus something is there which is a variable. So here we are adding only one, right? What we can really do is that we can really optimize the circuit. Instead of this preset, there is one signal, I mean I don't know, XR or whatever, again maybe it's a 2-bit signals or whatever. So then we have to synthesize a complete different, full kind of adder. But since we are adding only one, what we can really do is that we can really minimize the logic. So how do we really do that? And again, so I mean it will take some time, but you see, right? So we have a 0, right? Preset could be 0. So plus 1 means what? 1, right? So 0 0 1, right? And again it's a 0 0 1 means we added 1, right? So we have 0 0 1 0, right? So now what you do is that you draw the kind of complete, let's say the truth table, and you get the equation for C out 0, C out 1, 2, 3, draw the diagram. So that itself is your synthesized diagram. I mean you try to do it at home and you will get these equations, and you can check with what we have here. And again, as I said, right, so the diagram which you have may not really match with this one, but you look at the expressions here, because as I said in the book, right, he used what is known as this AOA gates, OA gates. That's what the library has it, but doesn't matter, right? As I said, the synthesis output really depends upon what you give as input. I mean in this library he has this OA gates, AOA gates, and or invert and all. I presume answer has converted, and let's say talked about these things in the digital CMOS VLSI design, right? So if you look at, right, so this AND gate we have, right, A B bar, right, OR gate, right, so we have A plus B bar, right? So we have see, right, so OR we are trying to do the OR of the signals, and then right, and here we are trying to do the AND of the signals, and then negate. So this which way do you have question? Could be, no, I mean see, we can really optimize, right? So you are adding only one, right? So it's not like you are adding some kind of a generalized value, right? A 2, 3 or something, right? So here you are adding only one. It's not like you are adding, let's say 2 or 3 which can really variable. So here, right, so then we can really optimize. So I think sometime I think answer asked it's one question in one of the presentation, right? if you are multiplying by only 2, but now the multiplies a plus, let's say a multiplied by 2, right, we can just optimize the circuit, but a multiplied by b, I mean b value could be anything, right, we cannot optimize unless we know the value of b, right. So that's the same thing here, okay, good. That's fine. So there are some more things, okay, the logical operators, right, the logical operators exactly translate to the gates, so we don't have to talk about that. When you have these arithmetic circuits, right, we have signed and unsigned operation, right. So I mean in arithmetic case, right, signed or unsigned doesn't matter anything, right, I mean doesn't make any sense, right. Only thing is that it's the same adder, but inputs are really represented in signed, let's say 2's complement form. Yeah, good. So let's skip those slides. Okay, relation, equality, okay, fine, okay, this is also fine, okay. I mean, okay, what we'll do, okay, so there is a conditional expressions, right, if and else, okay. So again take a minute or two and think about what comes out of this logic. So try to really draw the diagram with respect to the signals, and again as I said, right, all the operators, logical operators will result in a kind of a translation to gates. Right, so here you need to calculate the XR of this one if this condition is true, else this one. So basically, of course, it's a kind of a multiplexer where to the one input this goes, 0 input this goes, yeah, and of course, right, the condition is not reset, and of course the diagram might look different, but it's exactly what we talked about, something like this, right. So the condition itself is not reset. We have 1 and 0, 1 is connected to this one and 0 is connected to this logic, right. Okay, so that's also fine, okay, okay. Okay, now yes, right, hardware you have no, here if you see, right, on the hardware you have to perform this one and perform this one, and then it's a combination logic, right, it's again the left hand side has to really drive the right hand side always. So right, so I always execute, right, and of course it based on the register signal I will select. But again, do you have a control over the reset? If you know already that reset is a constant value, then I don't need this expression, right. But here the question is that you do not have a control of reset. Reset could be input, right, it's someone else gives you, but already if you know the reset value, we don't need this expression, right. Either we can just compute the either true value or false value, that's all. But you see, right, we do not know what value we need, right, and it all depends upon the reset. Yes. I mean again maybe we have to modify the code, okay, and I understand what you are trying to say, that it's kind of again a latch, you right, if the reset equal there, then only you evaluate and pass it on. So then can be done, but again you see, right, it's a pure combination logic. So okay, good. Okay, now there are few important things we'll do. Okay, so here again, can you think of a kind of a logic diagram for this one? Very good. Okay, now so for instance A and B, right, so what is the way it is saying is that, I mean you see think in terms of not gates but bit higher components, right. So this could be select signal, right. So maybe I will giving this A and B to some kind of a comparator, and now whether this A greater than B, that will come as input. It could be true, it could be false. If it's true, I will assign A here, if it's false I will assign B, and this is Z. Okay, now whatever you have is exactly the same logic. Okay, and now later on you just try to really derive the equation and just try to check it will match. Okay, good. Right. So now here again something simple, right? Something similar, but in this case we have this is a control, right? It's a true and false. What is my output? Z. Input side I have this A and B, here I have A or B, right? Yeah, good. Okay, again so this looks a bit different, but it's exactly the same. You can cross verify. Okay, now we can do this exercise. Okay, now again, so again look at the code, think about what is the possible outcome of this circuit, and this time let's kind of maybe solve it. So now here, is there a question of let's say flip flop? No, right? Since we don't have a passage or anything in the always, but there is a if, right? Okay, good. How many latches? The first question. Look at now what is the Z value, right? 3 latches, right? So now that means there will be 3 latches, and what is the latch enable condition? 5, right? 5 is 1 bit. That means you can expect in your circuit there will be 3 latches. Okay, all latches input, let's say enable pin connected to 5, right? You already know, and one latch output is Z0, Z within bracket 0, right? Z1 and another one, and Z2. Of course, right, just please watch out. So here we have used is a little Indian notation or big Indian notation? Big Indian, right? Normally, right, we will write 1:0, right? But we wrote it. Let's just watch it out. Okay, otherwise nothing, right? Okay, now how do I really derive the logic for Z0, Z1, Z2? So please think about what are the inputs, right? What are the inputs? Ones, right? So what is the ones value? 0, 1. I mean the bit size is 0 and 1, right? What are the values it can take? I mean 0, 0, 0, 1, 1, 0, 1, 1, right? Now once you add 1, what will be the output? I mean Z is the output, and of course Z is one more bit extra, right? 0, 1, 2, right? That means what you should do now? Write the truth table with ones as input, assume that you are adding 1 and come up with the truth table for Z0, Z1, Z2, right? And now in the output table what do you have? Z0 we have, Z1 we have, Z2 we have. So please tell me the expressions. That's all.